we have seen that the combined objective of achieving a required fundamental voltage, fundamental frequency voltage at the output, and mitigating some unwanted harmonics can be achieved by appropriately turning on and off the switches S1, S2, S3, S4. And these switching instants can be calculated offline by solving a set of nonlinear equations, and each equation corresponds to one particular condition. So much fundamental voltage is needed, so much third harmonic is needed. So after solving all these equations, one will get the switching angles alpha 1, alpha 2, alpha 3, and the switches can be turned on and off appropriately to give the required output voltage. But yeah, so this method is known as selective harmonic elimination, PWM. It is an offline PWM because the switching instants are calculated offline, not in real time. Okay, the opposite of offline is real time here, or on the go. However, this method requires some intensive calculations, so it has limited applications. So people started thinking about achieving these objectives in a better manner, and the better manner or the better method of switching can be understood by looking at individual leg, for example S1, S4, and the analysis will be easier or more convenient if we replace the DC source by two capacitors, and the midpoint of the connection is denoted by O. In fact, having this capacitance across DC input is a usual case, because this DC voltage must have been obtained by some kind of rectifier, which could have been followed by a DC-DC converter, and in both cases, either if it is a pure rectifier or a rectifier with DC-DC converter, there is going to be a capacitor at the output voltage. So having capacitors across this DC input is very close to the practical case, and instead of one single capacitor, we have split the capacitance into two, and we have defined the midpoint as O, as it could serve as a good reference point for our analysis. Let us consider one particular type of switching for the first leg whose midpoint is A. That means we are only looking at the switches S1 and S4. Here three patterns of switching S1 and S4 are shown. S1 is on for an interval of dTs. So in all these three patterns, one common thing is that what we are looking at is an interval of Ts. Okay, and within that interval of Ts, S1 is on for a duration of d times Ts, and S4 is on for the remaining time. And what are we looking at? We are looking at the voltage VAO, voltage of the point A with respect to the point O. When S1 is on, voltage VAO is VDC by 2, and when S4 is on, the voltage VAO is minus VDC by 2, that is by simple KVL. So VAO is equal to VDC by 2 for a duration of dTs, and VAO is minus VDC by 2 for a duration of 1 minus d times Ts. Let us look at the average value of VAO over this interval Ts. VAO average Ts, that is what it is denoted as, and that is equal to 2d minus 1 VDC by 2. It's a straightforward derivation, and we have shown three different cases of D here. D is equal to 0.5, D is greater than 0.5, and D is less than 0.5. When the duty cycle is equal to 0.5, what does it mean? When switches S1 and S4 are turned on for equal intervals in a small interval Ts, capital Ts, our average value of VAO will be 0. Then when the switch S1 is turned on for a longer duration than S4 within the same TS, VAO average over TS is positive. The first waveform has a positive average value. And when S1 is turned on for a shorter duration, or S4 is turned on for a longer time, the voltage VAO will have an average value which is negative, as shown in the third waveform. Now let us consider the case where we are looking at multiple intervals of TS. And what are we doing in these intervals? In a set of intervals of TS, we are generating pulses by appropriately turning on and off S1 and S4, and the width of these pulses is definitely different, and the duty ratios in successive intervals of TS is different. Here in the very first interval of TS, the duty cycle is 0.5. That means S1 is turned on for some duration and S4 is turned on for the same duration. For half of the TS, S1 is turned on, and in the remaining half, S4 is turned on. In the subsequent cycle of TS, subsequent interval of TS, our duty ratio is 0.7. That means S1 is turned on a little longer than before. In the next interval, S1 is turned on for even longer interval. That is why the duty cycle is 0.9. Then in the next or the fourth interval of TS, we are going back. We have reduced the duration for which S1 is on. So the duty cycle is 0.7. Then again it becomes 0.5. Then 0.3. Then 0.1. 0.3, and it reaches 0.5 again here. These intervals up to this, the intervals up to this point sum up to a duration of capital T1, and this pattern keeps repeating. The pattern of duty ratio keeps repeating, or the pattern of pulses having these kind of duty ratios keeps repeating over an interval of capital T1. Now let us look at the average value of VAO over each interval TS, smaller interval TS. In the first interval of TS, the average value of VAO is 0. In the next interval, where the duty cycle is 0.7, the average value is positive. And in the next interval, the average value is even more positive. Then the average value becomes a little lower, then it reaches back to 0. Now when the duty ratio is 0.3, the average value is negative because S1 is turned on for shorter duration. And when the duty cycle is 0.1, the average value even goes down, more negative. Then it will become less negative. Then the average value reaches back to 0 at the end of T1. And it can be noted that the average value of VAO over this complete interval T1 will be 0, because the duty cycle is starting at one point and going up and down and reaching back the same point. So the average value of VAO over complete T1 will be 0, but the average value of VAO over small interval TS is becoming positive and negative. What happens when our TS, the interval TS, is much smaller than the interval T1? And let us say we are taking a duty ratio. The duty ratio is varying, starting at 0.5, going all the way up to 1, and coming back to 0. In between it comes back to 0.5, and then it comes back to 0, and again reaches 0.5 by the end of T1. So let's say this is T1. For such a duty ratio variation, what will be our average value of VAO over small ts? It will have a variation shown like this. Why? Because average value of VAO over ts is simply 2d minus 1 times VDC by 2. So it is proportional to d, but it is just shifted because it's 2d minus 1. So if our duty ratio is varying in a sinusoidal fashion, our average value of VAO over ts will also vary sinusoidally as shown here. And interestingly, the average value of VAO over ts can be shown to be equal to the fundamental component of VAO mathematically. That means VAO will have a fundamental component which is just proportional to the duty cycle of that particular leg. Similarly, if you have another duty cycle which is varying sinusoidally for the leg B, VAO minus VBO is equal to VAB. So VAB will also have fundamental component which is defined by the duty cycle. Another interesting thing is that the same set of duty ratios can be achieved by lesser number of transitions. That is shown here in this figure. Let us consider the second cycle of TS. In the second cycle of TS, S1 has to be on for a longer duration and S4 has to be on for a shorter duration. So since S4 was on at the end of the first TS, if we continue to maintain that and then turn on S1, we save one switching transition. In fact, we save two switching transitions because S1 has to be turned on and S4 has to be turned off. So that those transitions are saved. And similarly, we can save switching transitions at each border of consecutive TS cycles, right? So even the second waveform shown here in red color will have the same average value VAO average TS, but it involves lesser number of switching transitions and thus it involves lower switching loss. So the conclusion here is that if we are able to generate a train of pulses which have the duty ratio varying sinusoidally, the train of pulses will have a fundamental component which is proportional to the duty cycle. But the question is, how do we generate these train of pulses, or how do we generate the pulses of duty ratio which is varying sinusoidally? That is the question.